Most of the world's environmental problems stems from human overpopulation. But if you look more specifically at the myriad assortment of environmental issues, I would strongly argue that it's the accessibility of clean water that is the most important environmental issue. You've seen images of the water cycle probably since about kindergarten. In general, all you need to know here is that there are multiple reservoirs of water. The reservoirs in the ocean, underground, on land, and in the atmosphere. And all these are in constant flux. When you look at the distribution of water on Earth, obviously most of that water is going to be within the oceans, more than 97%. Unfortunately, that's going to be saline water. It's salt water. Therefore, it's not useful for human consumption. If you look at the water that's considered fresh water, most of that is going to be locked up within glaciers. The remaining water, most of that is going to be within groundwater, and while we commonly see on the surface in lakes and streams, it's only a tiny, tiny fraction of a single percent. So most of the water on the planet is not available for human consumption. Now, when we think about the distribution of water on the surface, we can look at the land shape first of all, and we can see high areas called divides that will determine where water flows. And so water will flow from a divide into a drainage basin. And from an ecological standpoint, everything within a drainage basin is considered essentially a cohesive unit. And these units don't match up well with geographic boundaries. So when we look at this entire distribution of the drainage basin of the Mississippi River, we can break that down into smaller bits. So if you're within Springfield, if you're within Sangamon County, you're within the Illinois River Drainage Basin, which is part of the Upper Mississippi River Drainage Basin, which is part of the entire Mississippi River Drainage Basin. Anything that you spill into the ground here is going to eventually flow into the Gulf of Mexico. Now, when we look at a stream profile, this is a cutaway view of a stream. There's the head of a stream, which is where the stream begins. And that tends to be in the high elevation areas, the rocky areas, the mountainous areas. And it's going to flow very quickly through that high elevation area, that zone of sediment production or erosion. And it's that high energy flow that's causing that erosion. Within the zone of transportation, which is essentially what most of the state of Illinois is, sediments are being transported through. There's some erosion, there's some deposition, but overall there's a balance. Once you reach the zone of deposition, you're approaching the mouth of that stream. That's where it empties into an ocean or a larger lake. At that point, the angle of that river is very low. Therefore, there's very low energy. You no longer have the energy to carry sediment. So instead of being transported, all the sediment within the stream is being deposited. So again, we can look at the stream profile and think of a couple different characters that will consistently change when we go from the head on the far left to the mouth of a stream on the far right. The velocity will change. Higher velocity is closer to the head. Discharge will increase as you move toward the mouth, toward the right. And the channel size will also increase as you move toward the right. All three of these factors are effectively trying to do the same thing. They're trying to level the land to what's called base level. And in most cases, base level is going to be sea level. So the high velocity area is going to mean lots of erosion. It's wearing down those headland areas. A lot of discharge and a wide channel size means you're spreading out sediments near the mouth. So you're building up areas near the mouth and you're tearing down areas near the head. There are four major types of drainage patterns. By far the most common is going to be dendritic. Dendritic comes from the same word where we get dendrology, or the study of trees. So think of a dendritic pattern as a branching tree-like pattern. Dendritic patterns occur over areas where you have relatively uniform geology. There's not a whole lot of change, and there don't tend to be many fractures. There don't tend to be many faults in that area. Radial drainage patterns are areas where you have drainage away from a highland area, and that can be a volcano as shown in your textbook or any other kind of high feature. Rectangular drainage patterns occur in areas that have faulted rocks. When rocks fault, when they break, they don't just occur in one direction, but they tend to occur in one direction and then in a direction perpendicular to that rock. Therefore, you have this zigzag pattern within a rectangular drainage pattern in highly fractured, highly faulted areas. Trellis patterns can look somewhat similar. They form because you have tilted rocks, and so the river will break through some of these ridges and then flow parallel to some of these ridges of resistant rock. Now, when we start looking at the flow within the streams, there are two main types: laminar flow and turbulent flow. Laminar flow tends to be faster. Turbulent flow tends to be more violent. In the case of laminar flow, think of all the little particles of water moving in the same direction all at the same time. In turbulent flow, you have the situation that you see here in this image. You have chaotic flow, and there's water that's flowing downstream and upstream and to the sides and all over. So what determines whether you have laminar flow or turbulent flow? There are three main factors: gradient, the shape of the stream bed, and the discharge, meaning the amount of water that's coming down that stream. Of these, it's probably shape that is most important, but all these play a role. In the case of shape, if you have a nice smooth bottom, you tend to have more laminar flow. If you have a very rough bottom, it interrupts that flow, and so you cause a turbulent flow. Now, within that flow, whether it's turbulent or laminar, there are multiple ways in which you can move particles. Along the very bottom, you have the bed load, and that's where big things like gravel, cobbles are sliding and rolling across the surface. You have sand, which is not quite small enough to be suspended entirely within the water, and it's bouncing. So that's a process called saltation. The real small particles, the silt and clay, are within the suspended load. Okay. Finally, the ones that you can't see are the bits that are dissolved, and that's the dissolved load. So you have the three types of stream load: dissolved load, suspended load, and the bed load. Now, as you move from a high elevation stream where it's incised deeply within a rock, it moves toward the mouth, the river moves toward the mouth, and it tends to meander a little bit more. And so it creates a wide floodplain. Eventually, what you're going to see are a few different scars on the surface. You'll see areas of maximum velocity, which are going to be on the outside of curves, and that's where you'll have erosion. You'll have minimum velocity on the inside of curves, and that's where you have point bar deposition as opposed to erosion. And because this river can move back and forth or meander back and forth, we wind up with some features like Oxbow lakes and meander scars. And this animation does a better job of showing the creation of an Oxbow lake and a meander scar. Because of that erosion on the cut bank, eventually these folds, these curves within rivers, are going to connect. They're going to cut off a segment of water called the Oxbow Lake. And when that Oxbow Lake dries up, that's when we call it a meander scar. I like this figure a lot better than the animations. The next time you're on a plane, get a window seat and look outside. Especially if you're flying across the middle part of the United States, you'll see a lot of these meander scars. Even though you cannot see them from the surface, they're great and pretty cool to see from the sky. As water within a stream approaches the mouth, the gradient of the stream is very low. The sediment load is very high. Therefore, you have a lot of deposition going on. At the same time, you still have a lot of water coming into the system. Therefore, you have water that's trying to navigate new paths on a continual basis. This is called braided streams. You have lots of water pathways that are constantly changing because of the high amount of sediment. So you have a lot of these braided streams in delta situations. Closer to the head of a stream, you have individual channels that are coming together. Once you reach a delta, you have low gradient, and therefore the pathways are spreading out. So again, they're trying to distribute sediment in a way to flatten out the land surface. Now the same thing happens on land, although it's much less common. Anytime you have a change in the gradient of a stream, you essentially dump a lot of sediment. In the case of a mouth of a river, you have a change in gradient because the river is flowing into a body of water. In the case of an alluvial fan, you have a river flowing out of a mountainous region and hitting a flat region. Therefore, the velocity of the water decreases, meaning that it can no longer hold the same volume of sediment. Therefore, it dumps it, in this case, in the form of an alluvial fan. Now, if you look at the sides of a river, essentially the same thing is happening. As soon as water reaches the point where it overflows the banks, it loses its velocities, loses its energy, it loses its ability to hold all the sediment. Therefore, right on those edges is where a lot of sediment is deposited, especially the larger pieces. And then finer particles are deposited farther away on the floodplain. Now, over time, those are going to build up and form natural levees. If you live in the Midwest, you're also familiar with artificial levees, where by human activity we build up these ridges along rivers. Now, that is actually a serious environmental problem. It's a problem because rivers like to flood naturally. It's a normal activity. If you build levees, you're preventing them from flooding, and you're actually forcing that excess amount of water further downstream, which makes for more of a problem farther downstream. And the reality is levees will break. Levees will always break. So downstream you have more water, it breaks through the levees, and it causes more damage than if the river was allowed to flood normally. So moving into groundwater. This is what a lot of people think of when they think groundwater, an underwater river. And even though this is a really cool picture, this is not what groundwater, for the most part, is. Instead, it's a very small amount of water within a very small space. But that small amount of water actually adds up when you look at how much groundwater there is nationally and internationally. And it's extremely important. This is the largest available source of fresh water. So half the drinking water in the United States, half of the irrigation water in the United States is coming from groundwater. From a scientific perspective, groundwater causes erosion in good ways and in bad ways, and it equalizes stream flow. And we'll talk a little bit about both those in just a minute. From a biological perspective, which we will not talk much about, it provides some very unique habitats. So the first thing to cover when you discuss groundwater is the difference between porosity and permeability. So most groundwater is not underground rivers flowing. I mentioned it's that small amount of water that's between particles. Porosity is the amount of empty space between particles. It's not the same as permeability. Permeability is a measure of how interconnected those pore spaces are. You can have a big pore space, but if water can't get into it, it's not going to be able to store water. So it's that difference between porosity and permeability that is the difference between an aquitard and an aquifer. An aquifer is an area underground that is very permeable. An aquitard is not permeable. So if all the ground was equally permeable, water would flow onto the surface and simply seep into the earth. Okay? There would be no shallow groundwater for us to pump out. Well, that's not the reality. As you go deeper into the earth, you'll encounter layers that have lower porosity and, more importantly, lower permeability. So at that point, water can no longer seep into the earth and it has to accumulate. Okay, now this scenario here also is not realistic because we know the Earth's surface is not perfectly flat. So instead, what we see is a scenario where water seeps into the Earth, it accumulates on top of that aquitard, and it reaches the surface at streams, at swamps, at freshwater springs, and you'll notice that the groundwater surface is parallel to the land surface. Okay. So that groundwater surface is called the water table. Below the water table is the zone of saturation. That's where all the pore spaces that are permeable are filled with water. They're saturated with water. Above the water table is the zone of aeration, or the unsaturated zone. In this area, you still have some water, but not all the pore spaces are filled with water. So keep in mind that water has to pass through that zone of aeration, also known as the zone of, or the unsaturated zone, has to pass through that zone to get to the water table. So water is moving down through that layer toward the water table. It's also moving up via evaporation toward the surface to help form the soil moisture. So water is moving through that layer. It's not saturated in the pores, however. So when that water table encounters the Earth's surface, that's when we have streams. It's when we have springs. In the case of streams, we can have a gaining stream if the water table is sloped toward that stream surface. In that case, the groundwater is feeding the stream. If you look at the water table on the picture on the bottom, it's sloping away from that stream. In that case, the stream is a losing stream. Water is flowing from the stream into the ground. Now here's that other term that I mentioned, springs. It's another instance where the water table intersects the surface. And in many cases, it tends to be on more vertical surfaces than the boring case of a stream, like I showed you a minute ago. Hot springs are probably the most interesting kinds of springs. And there's a couple categories that we'll talk about. Most hot springs are going to form because of water being heated by igneous rock that is still cooling. And because that water is very hot, it's able to soak up lots of dissolved chemicals, and when it comes up to the surface, it quickly cools down, the water starts to evaporate, and all that chemical content is then precipitated out. Most commonly, it's going to form a rock called travertine, which is a type of calcite. Okay. Now what you see on these ledges are layers of travertine. So it's calcite or limestone, if you want to call it that. In the middle part of this picture, you'll also see some yellows and some greens. Now that's not mineral content, that's actually algae that's growing within the travertine. I mentioned that hot springs, and geysers as well, geysers are a certain type of hot springs, are typically formed from waters that are being warmed by the cooling of igneous rock. And you can see in the western United States where there's been more recent volcanic activity, that's where we have most of our hot springs. But if you look in the eastern part of the United States, you see some dots in Arkansas, in Georgia, in Virginia, West Virginia, and one up there in Pennsylvania. Those are areas that are typically called warm springs instead of hot springs. The difference is not just the temperature of the water, but how the water is warmed up. In the case of warm springs, water infiltrates into the ground, often via a fault line, and it goes deep into the ground. As you move deeper into the earth, you have higher temperatures. And so it's called geothermal warming. The water is warming up because of the depth within the earth. And then it's forced back up, and that new water is called a warm spring. In the case of hot springs, that water can be a couple hundred degrees. And that's especially true in the case of geysers. Geysers tend to explode because they're under great force. It's groundwater that is heating and expanding. It changes to steam and then it erupts. Now the key difference between a geyser and other hot springs is how the plumbing works. In most hot springs, the big opening is not going to allow pressure to build up. In the case of geysers, there's an opening underground, a cavity where the water can accumulate, the cavity where the steam can accumulate, but there's only a very small opening at the surface. Now, instead of springs and hot springs and geysers, most of the way that we encounter groundwater is by pumping wells. And so we can drill a well and start pumping. Now, immediately what's going to happen is that the water table is going to dip toward that well. It's called a cone of depression. So this is a three-dimensional depressed area on the water table. This forms because even though water is trying to replace the water that we're pumping out, we can pump a lot faster than water can flow underground. Okay. So in areas where the water flows more slowly, the cone of depression will be even larger. Now this is a problem because if you're a small water user and your well doesn't go deep enough, and your neighbor has a well that's pumping even more, that cone of depression can intersect your well and can actually pull that water table below where your well is. So what do you do at this point? Well, so far in the eastern United States, this has not been a major issue outside of Florida. It has been a major issue in the western part of the United States. And there are laws in many of the western states governing how deep you can drill your well and how fast you can pump, because that cone of depression doesn't just affect you, it affects the water table of your neighbors. So in the case of wells, we're typically pumping water up. But in some cases, water is going to rise up within a well naturally. So it may seem like water is defying gravity, such as in this case, a well is drilled and water rises up, although not all the way to the surface. So is it defying gravity? Well, obviously no, it's not. It follows a principle that you may have experimented with a little bit yourself. So if you put some apple juice into a funnel, when you raise one end of the funnel, the apple juice in the other end is going to rise up to the same level. So if you rise the funnel end all the way up and put the open end into your mouth, the water is going to flow via gravity into your mouth, even if your funnel is still pointing, even if your drinking end is still pointing up. Now the same thing happens underground. So water that flows up within a well on its own pressure is an artesian well. If it flows all the way up to the surface, it's a flowing well. If it just moves up a little bit, but not all the way to the surface, it's called a non-flowing well. Now this is obviously an old photograph, but it's one that I find very impressive. In central and southern Texas in the 1800s, desert area or very dry areas, but when people started drilling for water, they hit an aquifer. They created artesian wells, and these artesian wells had so much pressure that they were shooting water up 20 and 30 feet into the air. So this was fantastic. They could build cities around these artesian wells with this phenomenal amount of water. The problem is, eventually that pressure is relieved. So after about 1 year of all these wells flowing around San Antonio, they were no longer spilling out onto the surface. There are still some places in central Texas and Florida and a few other places around the U.S. where you can have artesian wells, but they're obviously going to be short-lived. The reason artesian wells work is because they are responding to gravity. The key is that all the water within an aquifer, that blue shaded area in the big picture on the top, all the water in there is trying to get to the same surface, trying to get to that same level. So if you're closer to well 1 over here, that water is not going to make it all the way to the surface. But if you drill a well in area 2, that water is trying to come up to that pressure surface. So that's that one surface where all the water is going to balance out because of gravity. Now, groundwater does a little bit of erosion, and it deposits a little bit of sediment as well. In the case of erosion, it creates caves, it creates caverns. Caves and caverns are the same thing. In the case of depositing material, it creates speleothems within the caves. So caves are formed when the groundwater is high. So groundwater has to be high to dissolve the underground rock. And in most cases, it's going to dissolve rock that is limestone. In some cases, gypsum. It's rarely going to dissolve other types of rocks. Once the water table lowers and that cave is open to air, that's when deposition starts to happen. Water dripping into the cave can form speleothems. Speleo means cave, thems means things. So speleothem is anything in a cave. Stalactites and stalagmites are the two most general types of speleothems. Although if you go to a cave, you'll hear lots of terms like soda straws and french fries and cave bacon. Basically, categorize everything as a stalactite, something that's hanging tight from the ceiling, tight from the cave roof, and a stalagmite, which forms from the floor and might eventually reach up to the ceiling. Now, one issue with that erosive capability of groundwater is that when it forms caves, caves are not stable. So the next time you go visit a cave, realize that that ceiling is going to fall at some point. It's going to happen because it no longer has water in it to keep that keep the roof up. Well, in the case of pumping excess amounts of groundwater, we do the same thing. We open up big cavities that are no longer supported by that water, and we can cause sinkholes, as you can see on the left. Or in more moderate cases, we can see subsidence. Subsidence being the gradual lowering of the land surface. So on the right, and in the course of about 50 years, you have the San Joaquin Valley of California lowered by about 30 feet. So this is a dramatic lowering of the land surface, and it's not just happening in the San Joaquin Valley. The same massive amount of lowering has happened in Houston and the Galveston area. Even more subsidence has happened in Mexico City. So we know that groundwater is a phenomenal resource for drinking water, for irrigation. However, we also know that it has potential problems if we pump out too much of it. There's another problem. Anything we dump on the surface can contaminate the groundwater. And I do see here that I misspelled the word contamination. So the contamination of groundwater is much more of a problem than the contamination of surface water. Because in the case of surface water, we can skim off the oil. We can block off part of it. In the case of groundwater, there's no way for us to go down there and to clean out every little pore space for an entire region. So in the case of groundwater contamination, it's essentially a permanent contamination. Once it's contaminated by sewage, by pesticides, by whatever, it's essentially contaminated for the lifetime of that aquifer.